In this video, we're going to talk about how temperature and molecular velocity are related. And so we're going to go back to our talk on kinetic molecular theory for this. And we said gases, the only difference between gases are their masses. But we said that, even though they have different masses, all gases will have the same kinetic energy at a given temperature. And so let's look at our equation for kinetic energy. Kinetic energy equals 1/2 mass times velocity squared. Therefore, velocity is inversely proportional to mass. On average, at the same temperature, since all gases have the same kinetic energy, lighter particles travel faster on average than heavier ones. And heavier particles likewise travel slower than lighter ones. And we can measure this, and it's called the root, not the room. The root mean squared velocity. And that's just basically, on average, what is your velocity? And this mu squared is just the average of the particle velocity. So this is just saying, on average, how fast are you going? So let's talk about temperature and velocity now. So for kinetic energy of 1 mole of gas, we have on average, it's 1/2 the molar mass times the mass times this mu squared, which is the square of the particle velocity. Now, we said in kinetic molecular theory that the average kinetic energy of a gas is proportional to temperature. Higher the energy, then the higher the temperature. We don't want that proportional because we can't really use it. So we have to use the gas constant instead. And we'll say kinetic energy on average equals 3/2 RT. Don't worry about where that 3/2 comes from. Now, we can combine our two equations, our kinetic energy equations, and we get this equation. And we do more math. And I'm not really interested that you know how to do all these steps. That's for a math class. If you are a person who really understands how something is by going through the math of it, here it is. But what I want you to know is that the average root mean squared velocity of a molecule or a gas molecule equals the square root of 3 times the gas constant times temperature divided by molar mass. And that's why I have stars around here. This is the equation you need to know how to use. You don't need to use any of these. Just have to use the one with the stars around it. So let's use this equation and see what type of problems we can use it for. So I want to know, what is the root mean squared velocity of oxygen and water at 298 K? So oxygen's a gas as well. For this, we're going to use the gas constant of 8.314, where it has joules. And note, 1 joule is 1 kilogram per meter squared second squared. I have the molar masses of oxygen and water here. So see if you can't figure out the root mean squared of oxygen and water. All right, let's take a look at the answers for this. We're going to start with oxygen. And before we do anything, let's just look at the units. So we have 3 times the gas constant. And here's the units of the gas constant, times the temperature divided by molar mass, which I'm going to have in kilograms. So kilograms cancel out, moles cancel out, temperature cancels out. We're left with meter squared per second squared. We're going to square root that whole answer. So our answer is going to be meter per second, which is a velocity. So let's plug our numbers in there now. 8.314 for our gas constant, temperature 298. And we have to do kilograms per mole, so it's 0.032. And our speed is 482 meters per second. Do the same thing for H2O. That is not O2, but that's H2O. we get 643 meters per second. And this makes sense. H2O is lighter, so if it has the same kinetic energy, it should be faster. And here's a graph that shows it. Here we have 5 different gases, O2 being the heaviest, H2 being the lightest. We have velocity on the x-axis and just a percentage on the y-axis. You can see on average your lightest gas is the fastest and your heaviest gas is the slowest. Now let's just look at N2 gases at different temperature. At higher temperatures, which is shown here, gases have more kinetic energy on average. Therefore, on average, they move faster. But that is how you use root mean squared for your calculations. And that's it for this video, and I will see you in the next video.